Hello friends, welcome back to my channel. Through the clash of the space race between the US and Soviet Association, the two associations explored different avenues regarding striking and trial advancements, chasing the information and shrewdness expected to vanquish this new wilderness. The assignment of get together this information itself was a gigantic test that necessary a new airplane, equipped for arriving at the edge of the room and pushing the limits of humans getting it. One plane that stands apart during the rising of the space race was the X-15. A plane intended to be quick to break into the hypersonic system and move past the Kármán line, 100 kilometers over the world's surface, and break into space. The plane would assist NASA with fostering the materials expected to endure the serious intensity of reemergence. The designs need to guarantee steadiness and control in the hypersonic flight system and the improvement of control components for the vacuum of room, while giving the impulse to foster a few innovations expected to permit people to get by. The vacuum of room, similar to the first of its sort completely compressed space suit. This was the world's most memorable space plane. 1. The plane laid the basis for both the Apollo program, space transport, and the State Route 71. Right up until now, the plane holds the record for the quickest at any point maintained trip with a top speed of 6.7 Mach, leaving even the State Route 71 in the residue as this rocket-controlled plane fueled through into the edge of the room. This is the crazy design of the X-15. At the point when the X-15 was first proposed during the 1950s, no other airplane came really near its proposed capacities in both max elevation and max speed. The nearest any past plane came was the X-2, which finished out at a maximum speed of Mach 3.2, not exactly 50% of the inevitable record the X-15 would accomplish. The X-15 wasn't simply a step in the right direction in capacities, it was a colossal jump that would require the best personalities in NASA, or the NACA as it was called then, at that point. The initial step on this street to the record 6.7 Mach was fostering a motor equipped for driving such an airplane. Also, for this, the architects needed to go to rocket impetus. Indeed, even the high-level crossover motors of the yet-to-be-created State Route 71 couldn't drive into the hypersonic system, and no air-breathing motor would have the option to work at the elevations the X-15 was focusing on. The architects knew the motor they required would have to deliver around 240 kilonewtons of push-to-drift level with a capacity to change push yield while squeezing into the limited body of the plane. There was no such thing as this strong motor, and creating it would demonstrate to be quite possibly the best test confronting the X-15. The main issue to address was this variable push yield, which was wanted to give pilots more command over the airplane and take into consideration testing at different paces. Impacting straight into the hypersonic system without broad testing at lower rates would have demonstrated terrible as the challenges of frictional warming were settled. More seasoned motors, similar to those of the Chime X-1, the main plane to break the sound wall, accomplished variable power yield by basically specifically touching off 4 separate burning chambers. This given ventured power yield, however, false choke. The X-15 required better control than this and expected to accomplish it without adding huge weight and intricacy to the motor. Added intricacy would diminish the security, putting any pilot in harm's way, while any additional weight would fundamentally decrease the most extreme elevation the plane could accomplish. The X-15 accomplished this control by shifting the speed of its turbopump, which is the siphon that powers the oxidizer and fuel from their particular stockpiling tanks into the burning chamber. Siphoning liquid at the rate a rocket drinks is really a hugely troublesome test. The X-15 conveyed 8,165 kilograms of fuel and oxidizer, which the plane consumed in only 85 seconds. That is 5,897 kilograms each moment. That errand would require a strong siphon, and that siphon would require a strong energy source. Presently, it might appear to be an undeniable decision to just utilize a part of that rocket fuel to power the siphon, and without a doubt, this is how current rockets, similar to the SpaceX Merlin motor, power their turbopumps. 3. Turbopumps work by turning a turbine utilizing hot quick streaming gas, however, utilizing the items of rocket fuel burning in a turning turbine would rapidly prompt seriously softened and broken turbines. The burning results of rocket fuel are excessively hot for this application. The Merlin motor gets around this by utilizing a very fuel-rich combination for the turbopump pre-burner, which prompts fragmented ignition and lower exhaust temperatures. That exhaust has a huge piece of valuable fuel held inside it. However, the dingy exhaust isn't reasonable for expansion to the central purpose chamber. In this way, that fuel is unloaded over the edge. You can see that fuel-rich dingy gas coming out of this fumes here on the Merlin motor. The X-15 utilized a completely different fuel to drive its turbopump. A monopropellant in the type of hydrogen peroxide. A monopropellant, similar to hydrogen peroxide, decays in an exothermic response when within the sight of an impetus. For this situation, hydrogen peroxide was passed through a cinema impetus which caused the hydrogen peroxide to deteriorate into oxygen. Furthermore, superheated 737-degree steam was. It was this superheated steam that drove the turbine. Furthermore, the speed of the turbine could be constrained by basically changing how much hydrogen peroxide, ignoring the silver impetus with the utilization of control valves. The exhaust of this framework was then essentially unloaded over the edge through this exhaust port. This was by all accounts not the only use for hydrogen peroxide on the X-15. A comparative framework fueled the helper power framework, or APU, which controlled the plane's gadgets. The pilot would likewise require some type of control when beyond Earth's climate, where the plane's streamlined control surfaces would never again work, so the plane was fitted with engines on the wingtips and nose to give control while in space. These engines were additionally fueled by hydrogen peroxide. Utilizing hydrogen peroxide to control the turbopump accompanied a few difficulties. This turbine worked two separate impellers, one for the fluid oxygen stockpiling tank, which worked at 13,000 RPM, and one for the anhydrous smelling salts tank, which worked at 20,790 RPM. These unique siphoning speeds ran on a similar drive shaft, which required outfitting to accomplish the suitable fuel blends, yet in addition consolidated serious security worries over coincidentally fuel spillage from the particular hydrogen peroxide, fluid oxygen, and anhydrous alkali lines, as a turning shaft is more challenging to guarantee sufficient fixing. Twofold seals were set between each part with the end goal to forestall blending, while an arrangement of compressed helium cleansed the framework. The decision between fluid oxygen and anhydrous smelling salts was a fascinating one. This motor required to have been strong, incredibly strong, and getting it to the expected push levels. Planned to require the right fuel and oxidizer blend. Page 95 of Ignition. While talking about rocket power abilities, one of the principal stops is explicit motivation. Explicit drive depicts how productively a fuel can change over its mass into push. To comprehend this, how about we first gander at complete drive, which depicts the push force produced over the whole consumed time of the motor. We can diagram this somewhat effectively by plotting the push the motor is giving in each second of its flight, which might look something like this. The absolute drive is found by finding the region under this diagram, which gives us the absolute energy the rocket delivered. This is a helpful measurement in itself, however unambiguous motivation is better, because not all forces are conceived equivalent. Two different fuel and oxidizer mixes co-oxidize a similar aggregate. Motivation, however, we want to think about the heaviness of the fuel and oxidizers themselves, later. The underlying load of rockets is constantly overwhelmed by the heaviness of their fuel. To find the typical explicit drive, we partition the complete motivation by the absolute force weight the rocket removed. 4. Going by this measurement, a fluid hydrogen and fluid oxygen fuel combination are by a wide margin the best. Hydrogen has the least subatomic load of any known substance, with every hydrogen molecule comprising of only one electron and one proton. The H2 particles utilized in fluid hydrogen fuel have a subatomic load of only 2.016, while RP-1, the lamp oil inferred fuel utilized for the SpaceX Merlin motor, has a subatomic weight of around 175. 5. Be that as it may, subatomic weight isn't the main consideration deciding explicit motivation. We likewise need to consider a large number of different elements like fuel blend proportions, ignition temperatures, pressure proportions, and explicit intensity proportions. 8. This is where a decent straightforward explicit motivation esteem provides us with a reasonable comprehension of how much push per unit weight of fuel. Also, oxidizer blend might give, without diving a lot into the confounded material science and science. Also, seeing this worth, hydrogen is awesome at about 381 seconds adrift level, while the lamp fuel and oxygen blend of the Merlin motor has a particular drive of about 289 seconds. 6. Nonetheless, it's by and by not quite as straightforward as picking the most elevated explicit drive esteem. Since hydrogen has an exceptionally low thickness, meaning we want a lot bigger volume tank, it's likewise a troublesome fuel to deal with, as it will bubble off whenever permitted to transcend its very cool limit of short 250 degrees Celsius, requiring protection, bubble-off valves, and last-moment energizing. For sure, this minuscule particle can leak out of the smallest of openings, even the holes between bigger particles of apparently strong metal. Despite its true capacity, hydrogen was not prepared for this assignment, but rather would before long be put to use for the absolute first time with the Centaur upper stage after numerous long stretches of advancement hiccups. There was a lot of trial and error during this period to track down a fuel and oxidizer blend that would give the particular motivation expected to get the plane to hypersonic speeds. What's more, it wasn't simply an issue of stacking the most impressive fuel and oxidizer blends into the gas tanks. Expanding the particular motivation is straightforwardly connected to raised ignition chamber temperatures. Since energizers with higher motivations for the most part discharge more energy when touched off. This is one of the significant obstacles designers of this time needed to battle with, as the materials. What's more, plans expected to endure these outrageous temperatures didn't as yet exist. The conventional fuel of the time was a 75% liquor and 25% water combination with a fluid oxygen oxidizer, which has a particular drive of around 269 seconds. Not sufficiently high. The water was added into this blend basically to lessen the burning chamber temperature, which obviously decreased the drive of the motor. 9. To accomplish that higher explicit drive, the specialists expected to sort out a method for permitting the motor to endure the raised temperatures that would accompany a higher drive fuel. Furthermore, the best way to improve materials or track down a method of effectively cooling the motor. In a perfect world, both. One way they accomplished this was through regenerative cooling. Regenerative cooling utilizes one of the charges, typically the fuel, as a cooling liquid. The fuel will be siphoned through heat trade funneling that folds over parts presented to risky intensity, similar to the injector spout, push chamber, and spout, where it can draw heat away from the metals it interacts with, before being infused into the push chamber. This was not another idea, the V2 rocket, which utilized that 75-25 liquor combination too. Utilized regenerative cooling, yet the intensity move rates were not high. To be a successful cooling liquid, the fuel needs to have a high unambiguous intensity limit. Meaning, it can retain a great deal of intensity energy before its own temperature increases. Water has a high unambiguous intensity limit of around 4,200 joules for every kilogram Kelvin. Meaning it takes 4,200 joules of intensity energy to warm 1 kilogram of water by 1 Kelvin. 12. We too believe the liquid should have a high dormant intensity of vaporization, which simply implies it takes a great deal of energy to disintegrate the liquid. We don't need the liquid to transform into a gas. In the cooling tubes, here water has serious areas of strength for is, bubbling at 100 degrees Celsius, and that number will be considerably higher when it is siphoned under tension. So presently we are searching for a fuel that has a high unambiguous drive, yet with incredible cooling properties as well. Lamp oil was considered with a marginally superior explicit motivation of 289 over the conventional liquor/water creation, and was modest and unreservedly accessible at that point. Be that as it may, when gone through cooling tubes, lamp fuel of this time had a frightful propensity for framing clusters of contaminations. This cycle is called polymerization or coking, and sped up when presented to the intensity of the cooling tubes, which could stop up the slender cylinders and lead to a few significant issues. The RP1 grade lamp oil fuel we utilize today was created to battle this issue by eliminating the debasements from the fuel. Hydrazine, which has a particular drive of around 303, was likewise thought of, yet it had the terrible propensity for detonating when utilized in regenerative cooling, as its exothermic disintegration interaction can begin at a temperature as low as 97 degrees, which can prompt a rough blast. 10. In the long run, the specialists, who might have been short a couple of fingers right now, landed on anhydrous alkali as their fuel. Smelling salts is a fabulous cooling liquid with an incredibly high intensity limit, 4.6 to 6.7 kJ/kg.K, and high dormant intensity of vaporization, 1369 kJ/kg, making it the ideal rocket fuel for regenerative cooling, with a higher explicit motivation over its liquor/water progenitors. At 293 seconds. 13. Be that as it may, smelling salts accompanies its own issues. It's poisonous and would go after numerous metals, like copper. The tension checks of the X-15, which contained copper, were reliably fizzling following a half year of purpose, regardless of not being in that frame of mind with the fuel. This was irritating, yet considered an adequate compromise for the fuel's benefits. 14. This advancement cycle of the motor was laden with challenges and ran over both time and financial plan. In the meantime, the airframe needed to go through equal improvement without the last motor, rather utilizing two XLR-11 motors, which had recently controlled the Chime X1. These gave sufficient ability to get the plane to 3.3 Mach and test a portion of the plane's flight. Execution qualities, however, missed the mark concerning the prerequisites for hypersonic flight. 16. Meanwhile, information on hypersonic flight qualities of the X-15 were assembled, utilizing progressed hypersonic airstreams, yet the designers had no clue about whether this information would be precise. This was as yet an exceptionally new field of exploration. The plan and necessities of a hypersonic airplane that might actually fly into space were so fundamentally new and different that conventional streamlined features reading material must be left at the entryway. This plan to require a totally new methodology with all presumptions tossed out. During the improvement of the X-15, a discussion was seething in the NACA Ames research office over the plan of the nose for hypersonic airplane like this. Julian Allen contended that any airplane flying in this flight system ought to be planned with a dull body, something that totally got in the laid-out thought about the period, which requested for very directed noses and a work toward decreased drag. Julian Allen contended that this dull body configuration would make a bow shockwave which would make a limit layer of air around the vehicle and guaranteed the super frictional intensity was avoided the construction of the airplane and on second thought scattered innocuously into the environment. The X-15 integrated these thoughts into the plane's all driving edges, including the nose and wings. 15. And the thought would be applied to all re-emergence vehicles in future. As the X-15 re-emergence Earth's climate, it would be taking an exceptionally high approach way to deal with drain-off speed. An approach of 20 degrees delivered the upper vertical tail totally futile, as it was seriously safeguarded from windstream by the body of the airplane, though the lower tail would encounter an obvious expansion in viability as it plunged into the high-tension zone caused by the pressure side of the wing. So this lower tail was fundamental for guaranteeing yaw strength at these high approach re-emergences. In any case, this lower ventral tail was enormous to the point that it made setting down on the plane's more limited slides unthinkable, so the pilot needed to discard a part of it prior to landing. where it would send a parachute to land delicately, and ideally intact. The state of the X-15's vertical tail. X-15 is one of its most unmistakable elements of the plane. The crude-looking wedge profile seems to be something somebody might have planned, with 300-year-old information on liquid elements. Strangely, that is precisely exact thing is planned with. In 1687, Newton portrayed a condition, in his pivotal book Principia, that anticipated the power a level plate and a moving liquid would incite. He envisioned the air as a stream of particles that would strike the plate and move all of their energy typical to the surface and afterward head out lined up with the plate. He likewise expected the particles didn't cooperate with one another and there was no irregular movement. This, of course, is off base. The perplexing liquid fields in this present circumstance are considerably more confounded than Newton anticipated. However, strangely, his condition rather precisely approximates the powers on a streamlined surface and hypersonic stream. How about we take a gander at the wedge tail surface as it builds its Mach number? At supersonic speeds, a shock wave will shape at the place of the wing. This is called a slanted shock wave, and its point decreases as the Mach number increments, until, at hypersonic speeds, the point turns out to be little to such an extent that it nearly matches the wedge point. This looks strangely a great deal like what Newton anticipated for subsonic wind stream, and to be sure his condition turns out to be increasingly more precise as the Mach number increments. And keeping in mind that this wedge shape starts to act typically with this straightforward condition, ordinary flimsy bended aerofoils planned in light of subsonic liquid elements start to encounter a sensational misfortune of lift, delivering them basically pointless at hypersonic speeds. The wedge tail proceeds to perform and give the settling pressure expected to keep the plane flying straight. Nonetheless, this accompanies a trade-off of high drag, as the unpolished end makes a low pressure zone behind it that hauls the plane in reverse. However, this was of little concern for a short-reach plane that expected to dial back rapidly. The wedge tail was, as a matter of fact, fitted with extendable speed brakes to considerably assist this crushing impact while coming spirit from its rapid runs. Flying at hypersonic speed didn't simply accompany weird streamline features. The intensity of hypersonic speeds was perhaps of the biggest test that confronted the X-15. An extremely specific metal was required for this errand. The SR-71 used titanium, and it encountered a greatest temperature of around 300 degrees Celsius on its sharp nose and motor base spike during Mach 3 flight. This temperature was tremendously lower than what the X-15 was supposed to encounter at Mach 6 or more. The impact of frictional warming doesn't scale straightly. It wouldn't manage 600 degrees, yet as many as 1,000 degrees. A long ways past what the titanium skin of the SR-71 could deal with. Managing the limit outside heat was adequately troublesome, yet the creators likewise expected to battle with the outrageous virus exuding from the inward cryogenic fluid oxygen gas tanks. In pictures of the underside of the X-15 you can every now and again see ice covering the stomach of the plane where the fluid oxygen tanks are found. There's just a single metal on Earth up for this undertaking. Inconel X. Inconel X is a nickel, chromium, iron and niobium composite that was fit for working at lower temperatures, while having very great intensity obstruction. Plotting ductile yield stress against working temperature for aluminum, titanium and treated steel looks something like this. Presently, assuming we plot Inconel X, we can see exactly the way in which great it is at keeping up with its strength at incredibly high temperatures. Nonetheless, Inconel is weighty. Originators assessed that an Inconel X airframe would weigh about 180% in excess of an identical airframe produced using aluminum, and this was before the ablative materials were applied to consider most elevated speed runs. 18. The capacity to keep up with its solidarity at raised temperatures was useful, yet there were bound to be more issues to settle. Non-uniform intensity dissemination made obliging warm extension and stress very troublesome. Furthermore, a few overhauls of the plane's design was expected to fix issues that sprung up en route. During the plane's most memorable Mach 6 flight, 21, one of the quartz windows, worryingly, broke mid-flight when the Inconel outlining clasped because of warm development. Fortunately, just the external sheet broke and the pilot made do to tell the story. The outlining metals were instantly changed to titanium, which encounters lower warm extension, and the toward the back part of the outlining was eliminated for an exceptionally intriguing reason. The fashioners found during high-velocity tests that the plane was encountering outrageous neighborhood warming in unusual areas. One such problem area was showing up behind the window. Furthermore, it was the aftereffect of shock waves making violent stream. 20. These fierce streams made areas of raised heat move into the skin of the airplane that made hazardous problem areas. To find and take out these areas of interest, the planners utilized an extraordinary sort of intensity delicate paint that would change tone when presented to specific temperatures. After one high-velocity flight, the plane got back with wedge-molded designs exuding from the main edge extension joints, which were little holes in the main edge to forestall clasping when the Inconel X extended during flight. These holes were making this fierce stream, and to fix it, engineers introduced little portions of Inconel X over the extension joints. While trying to limit the tempestuous zones, they got more modest, however were not dispensed with totally. For the possible world record-breaking flight, the Inconel X alone wouldn't guarantee endurance of the plane. For this, the plane would require an ablative material, a conciliatory material, intended to consume and fall away from the airplane, pulling the intensity with it progressively. One of the chief missions of the X-15 was to foster these materials. Different materials and application frameworks were tried all through the X-15 program, and a lot of issues were found. Holding the ablative materials to the outer layer of the metal demonstrated troublesome. Some essentially tumbled off when the fundamental metal extended under it. Furthermore, it couldn't extend with it. These issues were found at more slow Mach 5 flights, however in the event that they showed up during the maximum velocity endeavor, the plane probably would have been lost. 22. Another issue emerged when the ablative material, in the wake of consuming with extreme heat from the nose of the plane, started connecting itself to the windows of the plane, making it very hard for the pilot of C, which was somewhat of an issue. The architects checked a few arrangements out to the issue. One included purposely detonating the external sheet of glass to eliminate the ablative stained piece and leaving just the inward sheet. The designers ultimately arrived on a safer arrangement by introducing a mechanical eyelid to the left window that stayed shut until the high-velocity piece of the flight closed, guaranteeing the pilot had something like one window to watch out of during landing. This was a generally crude arrangement and made some soundness issues, as once open, the eyelid behaved like a canard, and made the plane somewhat pitch up, roll right, and you're right. An irritating yet sensible issue. A somewhat seriously unnerving issue sprung up with the last ablative material. This pink material, called Mama 35S, was showered onto the outer layer of the plane in different thicknesses, as per the neighborhood need. It functioned admirably, however had one huge glaring downside. When blended in with fluid oxygen, the material would become unstable and could be set off by a slight effect. 23. A piece stressing considering the plane's oxidizer was fluid oxygen, and spillage was not intriguing, particularly as the plane must be constantly beaten up from its B-52 dock as it rose to elevation. The splash-on strategy might actually present the ablative material into the oxidizer lines as well. To limit this unnerving possibility, the plane was showered with an optional white sealant coat to forestall the fluid oxygen from blending in with the ablative, and accompanied the additional advantage or burden of stowing away the magnificent pink tone. Following 10 years of advancement, on the 188th trip of the X-15, the plane was at last prepared for its record-breaking flight. On October 3, 1967, William Knight climbed into the cockpit of the X-15, swinging from its roost under the breeze of the behemoth B-52, which conveyed the plane up to 45,000 feet. Here Knight dropped away and touched off the rocket motor, and with the assistance of 2 outer gas tanks, they thundered for 2.5 minutes, pushing the plane to the yet-to-be-broken record of 6.7 Mach flight. 24. In the endeavor, the plane was annihilated. The ablative covering hadn't functioned as well as trusted, and the plane arrived with parts of its skin softened away. Once more, it wouldn't fly. The leftover 2 planes in the program flew simply one more multiple times altogether before the program was closed down. Through the 199 trips of the X-15, NASA acquired the absolute most significant information it has at any point accumulated. The X-15 broke speed records, yet height records, when on July 17, 1962, Robert White turned into the primary man to fly a plane to space. The information NASA accumulated through this issue progressed our comprehension of rocket motor plan. Violent stream restricted warming, ablative materials, and hypersonic solidness and control. All of which added to the plan and advancement of Mercury, Gemini, Apollo. Furthermore, space transport programs, and gave Neil Armstrong, the pilot of the lunar lander and the first man on the moon, priceless involvement in controlling a rocket-fueled space apparatus. Armstrong was a captivating man. Somebody I had close to zero familiarity with until I watched this narrative on CuriosityStream. An hour and 40 brief narratives that had me enraptured the entire way through. I was enlivened by the narrative of a young man who became entranced by model airplanes at an early age and sought after that energy with each step of his life. If you like this video, please subscribe to our YouTube channel.